In this video, we're going to look at how to find some common confidence intervals using R. So before we start, there's a couple things that you'll want to make sure you have handy. So open here in RStudio, I have the R script for this module, so you'll want to have that R script open. As always, you'll also want to have the code book handy because we're going to be looking up different variables. And then you'll also want to have the note set that goes along with this video. So one of the things that you're going to notice in this video is we are going to use R to help us calculate the confidence intervals, but getting the values for the confidence interval is really just a piece of what we need to do. We need to make sure it's appropriate to calculate the confidence intervals, so we'll need to look at the variables and make sure that the assumptions are met for the central limit theorem. We may also have to make some changes to the variables or make some choices, so we'll want to be able to justify those choices. And then with any output that we get, we're going to want to interpret that output. In other words, give those numbers some meanings. And so the note set for this video has all of those pieces together combined with the output that we're going to get from R. And then of course you'll want to have that data set that you created for your state from Module 5 or the data set for Kentucky so that you can follow along. So I'm going to start out by just reading in that data set. So as always, I start by setting my working directory. This is the folder on my computer where I have the data set stored. Just like with the other videos, you'll want to set this to be the directory on your computer where you have the data set stored. And so as a reminder, there's a couple different ways you can do this. You could just copy this line of code from one of the previous scripts that you had it running, or if you come over here, you click on Files, we go to all the way over to the right, and I realize it is cut off of the video screen, but if you were to go a little bit further here off screen on your RStudio, you should see 3 tiny horizontal dots, and if you click on those, you'll see a file navigator open up. And then from here, what you'll do is you'll navigate to where on your computer you have the data set stored. And just as a reminder that this file navigator, the way that it works, it doesn't show you any of the files, it only shows you the folders. So don't worry if you can't find the folders. And so you'll navigate to that and you'll click on Open. That will open it here, and so I have mine open already, and you can click on More and then Set Working Directory, and that will auto-populate that line of code. And so you can always copy it from here, paste it up here, and then you'll have it for future use. I'm going to read in the data. I'm going to call it Kentucky 2020 data, and I'm going to read in that file. So again, same thing that we've done all along. And then it's always a good idea to view the data set. Again, this is just to make sure, kind of a quick glance, does anything look off? Maybe did something read in wrong? And then we always want to check over here to the right as well. I expect 2,869 observations out of 279 variables. So all of that checks out. It looks like what we've seen before, so we are good to go. So for the first confidence interval we are going to look at the confidence interval for a single mean. And so I'm going to pull the notes over here. And so here we have our notes. Make that a little bit bigger. Here we go. And so what confidence intervals allow us to do is they're one way for us to help to answer a research question. And so for each of these confidence intervals that we look at in this video, I'm first going to pose a research question, and then we're going to talk about how a confidence interval can help us answer that question. And so the first research question I'm going to look at is, what is the mean BMI of people living in Kentucky during the year? And I'll have to correct this. That should say 2020. I will correct that in your note set. All right, so a confidence interval for a single mean can provide an estimate of the mean BMI of people living in Kentucky. And we can use the 2020 BRFSS data, and we can use the code that's provided to find that 95% confidence interval. So a key idea here is that confidence intervals help us learn about means or proportions. And proportions are really a type of mean when you're working with categorical data. It does not help us learn about what's happening with an individual. And so that's a really important concept, that when we talk about our variables and confidence intervals, Confidence intervals help us understand what's happening on average. It gives us an overall picture. It doesn't tell us about the BMI of a specific individual, it just helps us learn about the average BMI. So let's see how we can do this in R. So the first thing that I'm going to do is I am going to read in the BMI variable. Now in your code book, the BMI variable starts with an underscore. So let's go to our code book and look at this variable. And remember, you can always hit either Control F or Command F if you're on a Mac. So I'm going to search for this variable. Mine is being just a little slow, so we'll give it just a moment here. Alright, so we see that this is the computed body mass. It does start with an underscore. Remember that R will not allow us to have a variable that starts with an underscore. So what happens is when that variable is read in, R places a capital X before it. So that's why here I'm calling the variable name with the capital X, and we've seen that before. All right, so looking here, we can see that this variable takes values 1 to 9,999, representing the BMI, and it has 2 implied decimal places. And then if it's blank, that means that we don't know, refused, or missing. So in other words, values that had those for the height and weight have been removed. All right, so let's just take an initial glance at this variable. So I'm going to read it in. I've named it BMI. You could name it BMI underscore var. You can really name it whatever you want. And I'm going to make just a quick histogram of it. Now, anytime we're going to run a confidence interval, it's always a good idea to take an initial look at the data. If it's quantitative, you could use a histogram. We'll see here in a little bit. If it's categorical, you can use a table. We just want to take an initial glance. And so you'll notice here, when I created the histogram, I didn't spend the time to change the colors or change the axis labels or any of that, because I'm really just trying to get an initial look at the variable. This isn't something I would put in a publication. This is just for me. So looking here, I can see we've got a slight right skew. I'm not terribly worried about that. But I notice here along the bottom that BMI is taking values like 2,000, 4,000, all the way up to 8,000. And these are unrealistic values for BMI. I know BMI is normally, like in the 20s, 40s, teens, those types of values. So if you remember from the code book, it said there were 2 implied decimal places. So what this means is a BMI where it's listed here as 2,000, that's really a 20. Okay, so they've just got 2 implied decimal places. So instead of putting 20.00, they've put in 2,000. Now, really what we would like to have is 20 instead of 2,000. And the reason for that is as we summarize this, we calculate the confidence intervals, really what our goal is to be able to present this information to other people. And so we don't want to have to explain that to them. We would rather have BMI in a format that they're used to. So what we can do for BMI is we can very easily just divide that by 100, and we're going to get the values in a format that we're used to. So I'm going to create a new variable called BMI corrected, and I'm going to take my original BMI and just divide that by 100. And then I'm going to create a histogram again of that corrected BMI. If we see here, notice the overall shape hasn't changed. That summary hasn't changed. The only thing that changed was here along the x-axis. Since we've divided everything by 100, we now have BMI in a format that we're used to. So if you'll remember, in order to create these confidence intervals, we're really relying on the central limit theorem in order to use the formulas that R is using in the background. So we want to make sure that we've met the requirements for the central limit theorem. One thing we need is a random sample, and we have that, but we also need a sample size. And so when we're working with a confidence interval for a single mean, a common kind of rule that we go by is we need 30 or more. And depending on the text, some texts may say 20, some may say 40, but it's going to be right around that. So here we're going to look at how many observations did we actually have. And so what this line of code is doing is we've seen the is.na before, and remember what that's going to do is it's going to go through and label all the ones that are missing. If you place an exclamation point in front of it, that actually negates it. So this is actually asking R, okay, which of the BMI corrected are not missing? In other words, which ones actually have values? And then we sum that, and that gives us the total. So we actually have 2,669 observations here, way greater than 30, so we've definitely met the central limit theorem. And so this gets to this really important point that whenever people collect samples and they want to estimate something, they think they need these massive sample sizes. We need thousands of people in order to do this kind of stuff. And you really don't. The required sample size is much larger, or probably much smaller than most people think. Like I said, in order for the central limit theorem to hold, we typically need about at least 30 people. So that's one thing to keep in mind. I think that's a common misconception that we see with data analysis. Now, since we're going to calculate a confidence interval for the mean, let's actually go ahead and find the mean of those BMI values. So we can see the mean here is 29.26979. And then next, we're going to calculate the confidence interval. Now notice here when I calculated the mean, I've got the NA.RM equals true. Remember, we always want to add that in because that's going to take out those missing values, and those can't be in there when we calculate means. In order to calculate the confidence interval, we're going to use what is called the t.test function, and it ends up, this is going to be the same function we're going to use next week to calculate hypothesis test as well, so that's why it's called a t.test. We're going to read in the variable, so we've got that BMI corrected. Just like with the mean function, I'm going to include that NA.RM equals true. And then I also need to include the confidence level. So the confidence level here, we're going to create a 95% confidence interval, so I've set that equal to 0.95. 95% confidence intervals are the most common, but that's not to say you can't make other kinds. Occasionally I'll see 90% confidence intervals used, but majority of the time it's going to be a 95% confidence interval. Now here, I haven't specified a one or a two-tail, so it is going to default to a two-tailed test. Oh, actually, forgive me, ignore what I just said. I'm skipping ahead to next week, so ignore what I just said. This is all that we need here. So let's run this. And here we get our output. Now the piece of output that we actually need here, because it gives us a bunch of things, it gives us both the confidence interval and the hypothesis test, is we actually just need this piece right here, which is the confidence interval. So now let's go back to our notes, and you'll see that I have copied that. Kind of compare them side by side here. I've copied that into your notes. So now let's see, what information do we need to include here to actually interpret this output. So it's always a good idea to leave a data note. So here I've left the data note that from the code book we know the value has 2 implied decimal places. That's just reminding me that I had to change something about that variable. Other data notes that you might need. So remember that some of the quantitative variables, they actually have numbers that represent the don't know, not sures. They haven't been removed already. So if you have to remove any of those values to make it quantitative, you would want to include that in your data note. Some of the variables code an 88, code a 0 as an 88. So if you had to change one of the values to 0 to make it make more sense, that's something else that you would put here in the data note. So basically any of those things that you're changing about the variable, and these would be the same things that you had to change when you created histograms of your variables. I'm going to include a note about the assumptions. What assumptions do we need to meet in order to make sure that these confidence intervals are going to be valid? So we needed that random sample, and we also needed to make sure the sample size requirement was met, and we have both of those here. So then we can write the conclusion of our confidence interval, and the conclusion is going to take that very familiar form that we saw in the notes. So here we're going to say we're 95% confident that the true mean BMI for the state of Kentucky was between 29.00 and 29.54 in the year 2020. So I have rounded that to 2 decimal places, which is pretty common. And so I added on this additional note here that says, note that an individual is considered overweight if BMI is greater than 25, and since all of the values in the interval are greater than 25, this suggests that on average Kentuckians were overweight in the year 2020. So again, keeping in mind that the confidence interval is not telling us about an individual BMI, it's telling us about BMI on average. And so you'll notice there in that language I'm constantly talking about BMI on average, and in that conclusion I'm giving the formal conclusion for a confidence interval. I'm stating stating what percent confident I am, I'm giving that interpretation, which has this very specific language. And we talk about that some in the notes, that really what's going on here is the interval is random. That's because the sample is random. And so we recognize that if we took a different sample, we may get a slightly different confidence interval. All right, let's look at our next type of confidence interval, which is a confidence interval for a single proportion. So here our research question is, what is the proportion of people living in Kentucky during the year 2020 who received a flu vaccine? And so a confidence interval for a single proportion can provide an estimate of the proportion of people living in Kentucky who receive a flu vaccine. And again, we're going to use our data and we're going to use R to find this confidence interval. So again, just like with the mean, notice this is telling us about the proportion of people who receive the flu vaccine, not about whether or not an individual is going to receive the flu vaccine. So let's go to our R code. So here I'm interested in the flu variable. That should be a 7, not a 6. And so we've worked with the flu variable before, so I've got flu var, and I'm going to call the flu shot 7 variable from the data set. So let's go and look at that variable in the code book. Right. And we're going to, there we go. And so this one looks at during the past 12 months, have you ever received the flu vaccine that was sprayed in your nose or flu shot injected in your arm? And so notice, so we've got a couple different values here. We've got a yes, we've got a no, we've got don't know, not sure, and we also have refusals. All right, so let's first make a table of that variable. So just like we made a quick histogram to look at the quantitative variable, here I'm going to make a quick table. So I'm not going to worry about changing the labels, anything like that. I just want a quick table so I can get kind of a snapshot of what this variable looks like. All right, so looking here, here is my 1, 2, 7, and 9s. So I can see 1,374 people said yes, 1,364 said no, we had 7 don't know, not sures, and we had 3 refusals. Now, when I go to calculate a confidence interval for a single proportion, what I have to do is I have to decide how I'm going to take this variable and dichotomize it. In other words, how do I break it into 2 separate groups? So how I'm going to break this variable up into 2 separate groups is I'm going to have one group that are my yeses, and then my second group is either going to be everybody that said no, or don't know, not sure, or refused. So this is my first choice that I have to make with this variable. And I just want to be clear when I report this out what the choices I made are. So you'll notice here I've made myself a note to remind myself of this here in my code. I'm going to group the no's, don't knows, not sure's into one group. Now another valid option here would be to set the don't knows and the refusals to missing and just compare the yeses to the no's. And of course you would want to document that and talk about that choice. So here's just you can go either way, but you just have to decide which choice you're going to make, and then make sure that you're clear in the choice that was made in your write-up. All right, so now in order to calculate a confidence interval for a single proportion, I have to give our 2 pieces of information. I have to give it the total number of responses, and then I have to give it the number of responses in the group that I'm interested in. So the group I'm interested in here is the yeses. Those are going to be represented by the K, and the total number is going to be the N. So you'll notice here I've got the sum, exclamation is dot NA, so this is very similar to what I did before with BMI. So I'm running it by itself first just so we can see what N is equal to, and we see that's 2,754, and then I'll run it with N, so you can now see N is assigned to that value over here on the right. So notice if we look at our flu table, if we add up these 3 values plus this value, you would get 2,754. So that is the sum of all of these. So again, if you just wanted to compare the yeses to the nos, you would take this value but subtract off the 16, which is the 13 plus the 3. And then to find the K, which is the number of yeses, I'm going to do something very similar, but here I'm going to find the sum that flu var is equal to 1, and then I'm always going to have that NA.RM equals true, and anytime I'm doing kind of calculation. And you can see K is equal to 1,374 here on the right, but again, looking at our tables, that was what the 1 was. So an alternative here is you could have just used your table and set K is equal to 1,374. The problem with that is it's easier to make mistakes later on. If you change this and you want to look at a different variable, you might forget to change that number. So that's one reason it's better just to stick with the variable names and just always change out all the variable names. And then we're going to do prop.test and give it the K and the N. All right, so here is our output. So again, just like with the quantitative variable, the output is going to give us both a hypothesis test, which we'll learn about next week, and it's going to give us a confidence interval. So the confidence interval piece is this part right here. So let's go back to our notes. So you'll notice I have that same output right here. And so let's look at our data notes, assumptions, and conclusions. So the most important data note I have here is what am I considering to be the complement to the yeses? And so here I decided to use the no's, the don't knows, and the refusals as the complement. If you decide just to use the no's, then you would say you're using the no's as the complement and that the don't knows and the refusals were removed from the data set. In terms of assumptions, in order for this confidence interval to be valid, we again need that we need that random sample. And we also need to make sure the sample size requirements are met. In other words, we need 2 in both the yes group and the complement of yes. Well, we obviously have far more than 10 because if you'll remember, looking at our table, our yes group had over 1,300, and then the complement of the yes, which the 3 of these added together, also obviously has more than 1,300. So then we've well more than met that sample size requirement. And so again, this goes back to this idea, there's this common misconception that we have to have massive sample sizes in order to do stuff like this, and we really don't because of that central limit theorem. So our conclusion here is that we are 95% confident that the true proportion of people in the state of Kentucky receiving a flu vaccine in the year 2020 was between 48.1%, and I realize like an extra percent sign, I'll fix that, and 51.78%. And so again, the confidence interval is telling us about what happens on average, and proportion is a type of average, and so it's not telling us about what any individual person is going to do, but it's giving us an idea on average what is happening in the state of Kentucky. Now, kind of as an interesting side note, at a previous semester when I taught this course, we used the 2018 data, and so when we used the 2018 data, actually these were the values that were found. And so it's interesting to look from 2018 to 2020 how much that confidence interval has increased. Whereas here, the confidence interval in 2020 actually contains 50%, which means it's plausible that 50% or more of people got their flu vaccine. Now that's only up to approximately 52%. It's not like it's plausible that 60 or 70% got their flu vaccine, but back in 2018, that entire interval was less than 50%. And so that suggests that less than half of Kentuckians received a flu vaccine in the year. And again, this is 2018. Sorry, I've got some typos in here. Again, this will be fixed on your end. So we do see an increase from 2018 to 2020 in terms of the proportion of people in Kentucky that are getting their flu shots. And it's not surprising because, COVID came between 2018 and 2020. So it's interesting that we can actually see, based on the data set that you're looking at, compared to the 2018 one, that it does seem like there's been a pretty good increase in the proportion of people that are getting their flu shots. All right, so our next one is we're now going to look at a confidence interval for a difference in means. So what this one is going to do, instead of looking at a single mean, it's going to look at a mean between two groups. And so here we're again going to work with BMI, but now we're going to compare it to those who report having good, better health compared to those that had fair, poor health during 2020. And so if we come here to the R script, the variable that we're going to look at is this RF health variable. So let's first go and look at that variable. And so for this variable, you'll notice if someone reports a 1, they say that they're having good or better health. and a 2 means they're having fair or poor health. So I've generalized that in the R script to just good and poor, but do know that the actual survey is in terms of good or better health and fair or poor health. So in the actual conclusion, we'll want to make sure to use that exact language. And then a 9 means don't know, not sure, refused, or missing. All right, so the first thing that I'm going to do in R is I'm going to break my BMI into 2 groups. I'm going to have the BMI for those that reported the good or better health, and I'm going to have BMI for those that reported the poor health. So the first thing I'm going to do is create my health bar. So this is going to store all that health information from the BRFSS, similar to what we've done in the past. And then what these 2 lines of code are going to do is they're going to take the BMI corrected variable that we created earlier, and they're going to pull out all the observations where someone reported their health bar was equal to 1. And then I'm going to create a group that has the poor health BMI scores. And again, it's going to take the BMI variable and it's going to pull out all of those people that reported a 2 to the health variable. So for your data set, what you're going to want to do is, you've got 2 different categorical variables here. So you've got one categorical and one quantitative variable. So you've got your quantitative variable, so for example BMI, and then your categorical variable. So your quantitative variable goes out front and your categorical variable goes on the inside, because that's what you're partitioning the 2 groups by. So next, just like we explored BMI individually, we're now going to explore it for each of the health types. So we're going to use the same code that we had up earlier. I'm going to create a histogram of those. Oops, I need to create these variables first. There we go. So this is the histogram of BMI for those that reported the good or better. Here's the histogram for the poor BMI. And I'm also going to look at the number of observations for each. So you'll notice that each group has more than 30 observations, so we're going to meet those sample size requirements for the central limit theorem. And then just like we did with the individual BMI, or the BMI by itself I should say, I'm going to look at the means. So here we've got the good BMI mean and the poor BMI mean. And again, I'm not saying that their BMI is good, I'm saying they were in that good health group or the poor health group. And we do see there's a little bit of a difference in the means. So up to this point, all I've really done is just repeated the code that we saw when we looked at BMI individually. It's just I've got duplicates of each one for each of the BMI for the 2 different groups. Now, in order to calculate the confidence interval for the difference in means, one decision that we have to make is whether or not the standard deviation of the BMI for each of the groups is equal to one another. And so I've got a little note here. So here we're going to just look at those 2 standard deviations. So when calculating the confidence interval for difference in means, again, you're going to have to decide if the population variances are equal or not. A general rule is to evaluate this using the sample standard deviations. If the largest sample standard deviation divided by, let me scroll over here, the smallest is greater than 2, then we use unequal variances. So looking at my 2, I can see that the good BMI was smaller than the poor BMI. So I'm going to take the larger, which is the poor BMI, divided by the smaller, which is the good BMI. I see that that is not greater than 2. So I'm going to calculate the confidence interval assuming equal standard deviations. I'm going to use the t.test again. I'm going to put in my good BMI and my poor BMI. So those are my 2 different variables. The order here doesn't really matter. You could do either way. You'll just want to be careful when you go to interpret your confidence interval that you keep the interpretation in the same order that you have it here. I'm going to set var.equal equal to true. If I didn't want to assume equal standard deviations, I would set this equal to false. So if you do this division and you get something greater than 2, set this equal to false. And again, I'm including that na.rm equal true. Okay. So again, I get some output that includes a hypothesis test as well as a confidence interval. I only need the confidence interval piece, so that's going to be this piece right here. Let's look at the notes. you'll notice that we have the same confidence interval here and here. So similar, we're first going to start with our data notes. So from the code book, we know the values have 2 implied decimal places. We saw that earlier with BMI. For our analysis, we're going to assume equal standard deviations. Your analysis may assume unequal standard deviations, depending on what you find with your actual values. And then we remove the responses from those that refuse to answer and unknowns for the health variable. And you might say, well, I don't remember removing those. How were they removed? Well, if we go back to the code, remember that when we created the good BMI and the poor BMI, we only looked at health variable when it was equal to 1 and equal to 2, so automatically the other ones got removed. For our assumption, we note that the sample was random and the sample size requirements are met since we have more than 30 in each of the different groups. And then so for our conclusion, we are 95% confident that the true mean BMI for people living in Kentucky with good, better health is between 2.78 and 1.49, less than the mean BMI for people living in Kentucky with fair, poor health. And so where did this come from? Notice that both of these values are negative, so that means that the second group is bigger than the first group. So that's why that we've got the first group is between this much and this much less than for the second group. And so notice, since the interval does not contain 0, it's not likely that the two means are going to be equal to one another. So we are seeing that those with good, better health, on average, have a lower BMI than those that have the fair, poor health, and that's, approximately between 2.78 and 1.49 points on average. Now, one thing that we always want to consider here when we report these, though, is that difference meaningful? So in other words, we can see this happening in the data, but is a difference in BMI of, let's say, 3 points, we'll go with the most extreme one here, is that really a huge difference in BMI? And so that's something you always want to think about too, especially with health-related data. As we find these differences and we see these changes, does that have an actual clinical difference to it, or is it so small that it doesn't really have what we consider useful meaning? And so note in the conclusion we say less because the two values are negative. If the two values were positive, we'd say more. And if the left was negative and the right was positive, we would say between this much less and the second value more. All right, we just have one more. We're going to look at a confidence interval for a difference in proportions now. And so the research question we might want to answer here is, what is the difference in the proportion of people living in Kentucky with good, better health who receive the flu vaccine compared to the proportion of people living in the Kentucky with fair, poor health who received the flu vaccine during the year 2020. So previously we had the two health groups and we compared BMI. Here we have the two health groups and we're going to compare the proportions that received the flu vaccine. And we can do this using a difference in proportions. So let's see how we do this with the code. So I've got some notes here similar to what we saw before. So I'm going to start out by creating two objects, one for good flu and one for poor flu. So just like we created the good and the poor BMI, these are the two groups for flu. And again, we're not saying good flu, we're saying the good, better health, or the fair, poor health. So similar to what we did with the BMI variable, we start with the variable out front and then our grouping variable here in the middle. We're going to look at a table of each of these groups. So here we have the flu vaccine status for those with the good, better health. Here we have the flu vaccine status for the poor. And so notice we had 1,025 yeses in the good group, 345 in the poor group. So what is good about these is you'll notice that those in good health had a much larger overall sample size compared to those in the poor. We can still do this confidence interval. That difference in sample size, it doesn't matter. We're still able to make that comparison as long as we meet those sample size requirements, which we have here. And this is one of the really nice things about comparing proportions is we don't have to have equal sample size between the good group and the poor group. To calculate the confidence interval, we're going to do pretty much the exact same thing that we did before. The only difference is we're doing it twice. And so you'll notice here I'm going to create an N and a K for the good. Here I'm just looking at the proportion. And so in the good health group, we had about 49% receive their flu vaccine. In the poor health group, we had about 53% receive their flu vaccine. And one way that if you wanted to justify that, that might seem not as intuitive, but those in fair poor health are probably going to the doctor more. They're probably receiving that reminder to get their flu shot more. So that could be, I'm not saying that explains that difference, but that could explain that difference. We're going to use the prop dot test again, but notice the difference is now for my X and my N, I'm going to give it the 2 Ks and the 2 Ns. All right, and here is our output. So again, if we go and we look at our notes, we see that same confidence interval we see in R. So we've got that same data note. Here we've got the proportion of those responding no, don't know, or refused as the complement, and we remove the responses that refuse to answer the unknowns for the variable RF for the health variable. And both of these are for reasons that we saw previously. We've met our central limit theorem assumptions, and then for our conclusion, we are 95% confident that the true proportion of people living in Kentucky with good, better health who received the flu vaccine is between 8.67% less to 0.32% more than the proportion of people living in Kentucky with fair poor health who received the flu vaccine during the year 2020. So note that since the interval contains 0, it is plausible that the two proportions are equal. So even though we saw that difference that when we looked at the proportions by themselves, the confidence interval tells us, it reminds us, hey, that's just what you saw in the sample. There is a possibility that in the population, these are actually equal to one another. And this kind of illustrates why confidence intervals are so important, because even though we see differences in the sample, that doesn't necessarily mean that those differences exist in the population. And confidence intervals kind of keep us in check, and they remind us of that by providing that full interval of plausible values to us. And so this is, again, another common misconception with data analysis that I see. People look at the raw proportions and automatically want to say that those two groups are different, but we need to remember we only looked at a sample, not the whole population. And so confidence intervals give us a way to account for that uncertainty and say, hey, even though we saw this in the sample, this might not be happening in the population. All right, so that concludes this note set with the R code. So as always, keep in mind that as you're working through these, the most important thing that you're wanting to do is to identify what variables you want to work with. And then, as far as the code goes, you really just need to change the variable names in and out. You don't need to change the rest of the code. Now, of course, if you come across something and you're like, hey, I want to do something additional, change this variable, feel free to ask me. I'll write that code. I'll help you do that. Or as always, if you have any, you're struggling with the code, you're hitting an error, you're not sure why, send those errors to me. I'm more than happy to help you troubleshoot your code.